All right, welcome back, everybody. So today we're going to talk a little bit more about potential flow, and we're actually going to start coding some things up in MATLAB, which will be kind of a nice change of pace to actually see some real like physical systems in action. Before doing that, just a few kind of administrative items. So the final exam is going to come out today after my office hours. So I'll post it right around 11:30, and it'll be due at about 5 p.m. on Friday. Okay, so to turn it in, you can either hand it in to me personally, you can slip it under my door, or you can put it in the Catalyst Dropbox. And if you do slip it under my door, please just send me and my TAs a quick email so that I know, like, I have a record that you actually did submit it. Okay. The exam will be 4 hours, just like last time. I would strongly recommend trying to take it in less time. Like, if this is preparing you for qualifying exams, I would try to take it in under 2 hours, and then you can go back and check your answers and make sure that you have everything. I took the exam last night, and it wasn't as hard as I thought, so that's good. But I did write the exam. So it's not super difficult, but it is completely cumulative. So there's stuff on ODEs, there's stuff on numerical analysis and calculus, vector calculus, pretty much everything we covered. So you'll need to know about your Taylor series and your finite difference derivatives and, order delta x squared error and things like that. Any questions about the exam? Yeah.
Will we be able to double check our answers with MATLAB like last time?
That's fine with me, yeah. Open notes like last time. You can use your homework solutions. I'd prefer you did not use the solutions that I posted online from other people. But all of the homework solutions are now posted. So homeworks 1 through 5, there are solutions on the website. So before you take the exam, you can, if there's something you weren't sure about, you can figure it out from there. Yeah, you can use the class notes, the videos, my PDF notes, your handwritten notes, whatever. That's fine. Just no internet, no books, no other people, no other people's homework solutions. Okay. Other questions about the exam? So I have to admit that writing exams is not my favorite thing, and it's not the thing I'm best at. I wrote a note when I was writing this last night that I should learn how to write better exams. And so I've decided to solicit an extra credit problem from all of you. So I haven't decided on the exact amount of extra credit, but usually what extra credit means to me is that if you're kind of on the border between a point grade, like a 3.6 and a 3.7, or a 3.7 and a 3.8, or a 2.8 and a 2.9, or whatever, then extra credit would kind of be the push you need to bump you to that next level. So the extra credit, this is not on the exam, this is completely separate, would essentially be to come up with your own final exam question. This could be on anything from the class, ODEs, linear algebra, numerical calculus, vector calculus. This can be something that you have seen in other classes. Like when you were undergrads, pick your favorite class, the best homework or exam problem you ever had. That's fine as long as you write it out and solve it. What I would really prefer are problems that have some physical motivation. Okay, so a neat one that I had when I was in vector calculus was this problem with ants walking on a donut. So the problem, this is a little too open-ended for an exam, but this is kind of the idea, is let's say that an ant is at point A, and the ant wants to get to point B. What is the shortest distance path on the donut from path A to path B, point A to point B? Okay, so this is a hard vector calculus problem. But it's easy to explain. It has a physical context. Like everyone understands the statement of the problem, even if you don't know how to solve it. Okay, so a good problem might be something like that, or But I just want to get ideas from you. So you guys are going to write my final exams for the next 5 years, hopefully. Okay. Okay. So anytime I think before next Friday would be fine. I'm going to assign grades next Friday. Okay, moving on. Other things. The exam is posted. I have office hours today. Extra credit problem. I think that's basically it. Are there any questions for me? I don't have a ton prepared today, so if there are any questions about anything, we do have some time. No? Okay. All right, good. So we're going to talk a bit more about potential flow, and I'm going to go a little deeper into the math, and then I'm going to go a lot more applied. And we're actually going to, hopefully the next 2 lectures are going to be a little bit satisfying in the sense that we're going to start with a PDE. And this is Laplace's equation. Okay, we're going to start with some PDE. And from this PDE, we're going to get a vector field. So one is we write down a PDE that has some properties we like. Right? We want a flow that has no rotation and is incompressible, for example. And then what we're going to do is get a vector field, V. And this is going to be a vector field in the plane of 2 spatial variables, x and y. And then 3, we're going to use V as the right-hand side for a particle's ODE, for a particle trajectory. So we're going to say something like x dot y dot is going to equal v1 of xy, v2 of xy. And we're actually going to integrate particles through this vector field, which was a solution to a PDE. Okay? And this is going to kind of round out all of the ideas in the class that we've had so far and really solidify why we care about vector fields, why Laplace's equation and potential flow are interesting, and how you can actually use them. Okay? Okay, so I'm pretty sure I've asked everybody this about 5 times, but just one more time, remind me how many of you have had some complex function theory, like some. Okay, so this is like about 15% of the class. Okay, so the first week of next quarter, I'm probably going to try to teach you as much complex analysis as I possibly can in 1 week. Okay, oftentimes people spend 3 weeks or 4 weeks on complex analysis in the second analysis class, and I think that's crazy. But there is a ton of useful stuff that I want you to know in complex analysis. And so I'm going to teach you, like the first week of next quarter is going to be pretty intense. I'm going to go like basically all of complex function theory that I can pack into 3 lectures. And we're going to start a little bit now. So we have 2D potential flow. And remember that our 2D potential flow had a couple of conditions. So we had this vector field V was given by the gradient of a potential phi. And phi had some properties. So, the divergence of V, I wanted it to equal 0. And I also wanted the curl of V to equal 0. And that's true if and only if the Laplacian of phi is equal to 0. Okay, so we derived this in the last lecture, that if I want to have this nice vector field V that's incompressible and irrotational, then it has to be the gradient of some special function phi that solves Laplace's equation. Okay, we know this from last time. Now, it turns out that there's another really, really special function. So phi is a special function. Phi is a very special function. Not all functions are as special as phi, called the potential function. And in problems like gravitation or electrostatics, it literally means the potential, right? The gravitational potential or the electrostatic potential. So this is not some like trick name. This is essentially like has the same meaning as in physics. But there's another special function. And this special function is closely related, and we'll talk about this next quarter. So another special function, psi, is called the stream function. And it's going to be useful because it essentially is going to tell me what streamlines are in my vector field. So if I followed a particle, it'll tell me where that particle goes and kind of like what the curve of particle trajectories are using the stream function. And so what I can do in lots of problems, I can write down a complex valued potential in terms of a complex variable z. So z is x plus iy. Okay, z is just a complex number, a complex variable. And this is going to equal phi of x and y plus I psi of x and y. Okay, I'm just writing down notation right now. I'm just telling you what the names of things are, and then we're going to tell you how to use these, okay? So we know that there's this special function phi. Phi is a function of x and y, and it's real valued. It's just a real valued scalar function. And I'm telling you that there is another special function called psi. It's also real valued, and it's a function of x and y. And psi also satisfies Laplace's equation. Okay? And so for lots of systems where you can write down this potential phi, there is also this stream function psi. Okay? And often it's going to be easier to get the vector field from the stream function than from the potential. And I'm going to kind of show you what this means in an example. So what we're going to be looking at here are complex functions of a complex variable. And we're going to split that function up into its real part and its imaginary part. And each of those are their own spatial scalar functions. And these potentials and stream functions are going to be really, really useful for telling us what the vector field looks like for physical systems. Okay? So let's probably start with an example. And remember, our vector field v equals v1, v2, and it equals partial phi partial x, partial phi partial y, which is just the gradient of phi. Remember, our vector field is equal to the gradient of our potential, which means it's just, the first x component is partial phi partial x, and the y component is partial phi partial y. And it turns out that if you can write down this special complex potential function, then this is also equal to minus partial psi partial y and partial psi partial x. So this is really, 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 really special. If I have this complex valued potential function that can be broken up into a scalar real valued potential plus an I times a scalar real valued stream function, and both of these functions satisfy Laplace's equation, then this is also true. Then I can get my velocity field v1, v2 either from my potential or from my stream function. Okay, just by taking partial derivatives. Okay, so a lot of really, really common... Okay, so for example, if I wanted to know what fluid flow did past a cylinder, right? If I wanted to know like what the streamlines were of some very slow flow past a cylinder, a solid cylinder, I could pick some special potential function that satisfied these boundary conditions, that the flow had to be 0 on the boundary. And I could then find the velocity field everywhere. And I can also do that for airfoils to find out what the streamlines are past an airfoil. Okay, so this is... I'm probably going to do this as a homework problem in the first week of next quarter, is actually have you derive the velocity field for these two problems from the potential function. But for right now, I'm going to start with a simpler set of examples. Okay? So oftentimes what we're going to do is we're going to take some complex valued variable z, and we're going to say this complex potential z is equal to z to the n. Okay? Now, z to the n is not that complicated for a complex variable. You just literally, like if I wanted z squared, I would literally take x plus iy times x plus iy, and I would get x squared plus 2I times xy plus I squared y squared, which is just minus y squared. And then I'd collect all of the real parts on one side and all of the imaginary parts on the other. And I'd say that this is x squared plus x squared minus y squared plus 2ixy. Okay, so in this case, x squared minus y squared would be my potential phi, and 2xy would be my stream function psi. Okay? And you can verify that this actually satisfies Laplace's equation. So these functions really do satisfy Laplace's equation. So phi of xy equals x squared minus y squared. Psi of xy equals 2xy. So let's just do a few things. So I'm telling you that this is a particularly useful potential. And if I change the power n, I can get lots of different cool vector fields. I'm going to show you a number of them. So this is kind of a great building block. This is a building block potential. And now what I've done is I've picked a power of 2. So my potential function is z squared. And we're going to work out this example for what the vector field, what the potential flow looks like for this potential when I take z squared. Okay? So first, let's verify, let's do a few things. So let's verify that phi and psi are both satisfy Laplace's equation. Okay? So first thing we're going to verify is that phi and psi satisfy Laplace's equation. Okay? Okay, so how do I do that? What are the steps I need to do to satisfy, to see if Laplace's equation is satisfied? Right, so I would basically take, I could take the gradient of phi and then take the divergence of it, or I could just compute the second partial derivative with respect to x and add it to the second partial derivative with respect to y. So let's just do that. Let's say partial squared phi partial x squared plus partial squared phi partial y squared equals what? Okay, what's the second partial derivative with respect to x? 2. Okay, and the second partial derivative with respect to y? Minus 2. Okay, so this is equal to 2 minus 2 equals 0. Okay, good. Laplace's equation holds. So in principle, the velocity field I get from this should be both irrotational and incompressible, right? Okay, let's also verify that psi satisfies Laplace's equation. So partial squared psi partial x squared plus partial psi squared partial y squared. Well, the second partial derivative with respect to x is 0, and the second partial derivative with respect to y is also 0 for psi. So this one's even easier. That's 0. So this is great. We verified that both of our potential function and stream function satisfy Laplace's equation. Okay. So now let's compute the induced velocity field. Let's compute v using the potential function, okay? So we're going to compute v. Okay, so v equals v1, v2, And it's given by the partial of phi with respect to x, which is 2x, right? And the partial of phi with respect to y, which is minus 2y. Okay, good. Seems reasonable. Let's also verify it by taking these partial derivatives with respect to the stream function. Okay? I feel like I messed something up here. Is there a negative I'm missing somewhere? Here? Let's say this should be down here. Okay. Good. Well, then that's obviously satisfied. Thank you. Right, so if I take the partial of my psi with respect to x, I get 2. With respect to y, I get 2x. And if I take minus partial psi with respect to x, I get minus 2y, which is my velocity potential. So I could get this either way from phi or from psi. Okay, good. So soon we're actually going to plot what this vector field looks like. But let's just for sanity's sake, because we haven't done this a single time yet, let's actually verify that this vector field is incompressible and irrotational. Okay, because I told you it's going to be. Let's actually convince ourselves that this is true. So 3 is going to be V is incompressible and irrotational. Okay, so let's do incompressible first. So divergence of V equals what? Well, it's the dot product of partial x and partial y with 2x and minus 2y. So that equals 2 minus 2 is 0. So we are definitely incompressible. Okay. And for irrotationality, let's say curl of V equals the determinant of partial x, partial y, partial z, and we have 2x minus 2y and 0. So the determinant of this is, in the I direction, we have partial of 0, and there's no z here, so the partial with respect to z is 0. So 0i. In the j direction, we have partial of 0 is 0, minus partial of 2x with respect to z is also 0. And the k direction is where it gets a little interesting, but it's not actually that interesting because partial of y with respect to x is 0, and partial of x with respect to y is also 0. Good. So we have irrotationality also. Okay? So what we're doing here is we're taking this fancy complex valued potential function. I've broken it up into its real valued function part and its complex valued function part, and I'm calling that the potential function and the stream function. And from the potential function and the stream function, since they both satisfy Laplace's equation, I get a vector field that's both irrotational and incompressible. Okay? So not all vector fields V can be written as the gradient of a potential. But special ones that can be written as a gradient of a Laplacian potential satisfy these properties. Okay, so now let's actually draw this thing. Any questions before we go deeper in the rabbit hole? No questions? Okay, maybe think about your questions. Okay, so now let's actually plot this vector field, right? So we had this potential, and now we have a vector field V equals V1, V2 equals 2x minus 2y. Okay, so Okay, what is the meaning of v1 and v2? Like, what does this vector field physically mean? Okay, so I have a velocity in the x direction and a velocity in the y direction. And these velocities are not just defined at one point, but they're defined at all spatial points x and y. Okay? So let's take an xy plane, and let's start drawing these vectors at a bunch of points x and y. Okay? So at the point 0, 0, what's my velocity field look like? 0. There's nothing happening here. That's a fixed point. Okay? What about at x equals 1, y equals 0? So I have a positive velocity only in the x direction. Okay, so here I have a positive velocity in the x direction. What about at a point way down in the x direction? Same, well, it's actually moving faster now, right? So it's actually a bigger vector moving outward, but only in the x direction. Similarly, in y, let's say I start with 1. What does this vector look like in the 0, 1 position? So just a negative y velocity, right? Because I have 0 x's and I have a positive 1 y, so I get negative 2 in this direction. So I get a negative vector here. Similarly, if I went down in y, I would be pointing up. And if I went left in x, I would be pointing left. And so on and so forth. What if I take a point like x equals 1, y equals 1? That's a weird one. So I'm going, so x equals 1, y equals 1. Then I would have 2 minus 2. So I'm going to the right 2 and down 2. So here I have kind of that kind of vector. Here I think I have a left vector. Here I probably have a vector that looks like that. Okay. And you can keep going, right? I just have these kinds of vectors. So I'm moving down on the y-axis. So in the y-axis, I'm moving towards the x-axis. If I'm on the x-axis, I'm moving away from the y-axis. And if I'm anywhere else, I'm kind of moving from the y-axis down to the x-axis. Okay? So is this starting to look familiar? Okay, what does this look like? This is a saddle point, okay? So if I said x dot equals v1 of x comma y, and y dot equals v2 of x comma y, or said another way, yeah, that's fine. Then this is just the same as x dot y dot equals 2, 0, 0, minus 2, xy. Okay? So what we have here is that so this is a vector field given by some potential function. Okay, we wrote the potential function down over there. And in this vector field, the potential it comes from phi is the solution to a PDE, Laplace's equation. So if I look at where a particle goes in this vector field, I get an ODE out. Okay, so this is an ODE induced by my velocity field. So I've been saying this a lot. The same thing is true if I have the fluid flow in the Gulf of Mexico, right? There's some partial differential equation that tells me what the velocity is going to have to look like at every point, right? There's some conservation of mass, momentum, and energy that give me PDEs. The solution of those PDEs gives me some vector field V. But then at the end of the day, what I use that vector field for is maybe I drop some blob of oil, and I see where that blob of oil goes. And I see that here, eventually it gets stretched in the, kind of compressed in the y direction. Probably should draw this a little better. It gets compressed in the y direction and stretched in the x direction. But because this is a potential flow, this is incompressible and irrotational. So the total volume of this blob of oil is going to be the same as the total volume of this blob of oil, right? Because it gets stretched in one direction, it gets compressed in the other. So that's what incompressibility means. And it's also not rotating. It's just getting sheared or stretched. Okay? So it's kind of cool. Super simple example, a nice potential function which is a complex number squared, and you get a saddle vector field, and you can really start thinking about what incompressibility and irrotationality means in this context. Okay, questions about this? I'll wait for a little bit. Any questions? Okay, so maybe this is clear. This is something we're going to revisit a lot more, so I wouldn't be too worried if this seems a little abstract. So there's a couple of things, if I was going to say where this confuses me, I just made up this potential, like, where did this potential come from? How did I know that this was a solution of Laplace's equation? I didn't tell you that at all, right? I just made this function up. I told you that this special function is going to give you potential functions and stream functions that definitely solve Laplace's equation. But I definitely did not tell you how that's true. And that's advanced, and that's something we'll talk about later. But that's something that you should be thinking about. So that would be a good question, is why does this complex potential guarantee that I'm going to have nice stream functions and potential functions that satisfy Laplace? Namely, why does this function give me irrotational and incompressible vector fields out? Okay? It's a weird question. It's like, I'm not sure I know the answer right now. I'm going to have to figure that out over the break. Sorry? I know it's true for lots of n. It's true for n equals 2/3 and 3/2, n equals -1 and 0, n equals 1 and 2. I haven't verified it for all n, but I would suspect the answer is definitely yes for positive n that are integers. Okay, yeah, so okay, I do know the answer to this. So if n is a positive integer, then this will definitely give you nice functions out. And the reason I know that is because for positive n, these will be continuously differentiable, and you can take all higher derivatives. You could take the 5th, the 6th, the 7th, the 9th, the billionth derivative of these, and they would be smooth and continuous. In fact, they would probably be 0, a lot of them, right? And so that means that this is an analytic function for positive integer n's. Okay? That's analytic means something very special in complex number theory. It means that these functions will satisfy Laplace's equation. That's basically what it means. And that means that I can write down this and this as equal. This is called the Cauchy-Riemann conditions. Okay, so this is something we'll talk about in the first week of next quarter. For z equals negative, for n equals negative numbers like 1 over z, 1 over z squared, 1 over z cubed, you get funky kinds of singularities at the origin. So everywhere else outside of the origin, your flow is going to be nice and incompressible and irrotational, but at the origin, you're going to have weird stuff happening. So you could have flows that actually do have a net circulation, a net, integrated vorticity because of what's happening at the singularity. Okay, that's called the Cauchy-Riemann integral theorem, and we're going to talk about that also, probably not in the first week. Sorry, it's called the residue theorem, for those of you who have done complex analysis. And then for weird fractional powers of n, all bets are off. Okay, so we're going to find that if I take the square root of a complex number, then I actually have two unique sets of solutions. And so you can get weird multi-valued functions when this is like 2/3 or 1/3 or 1/9 or things like that. But for positive powers of n, for positive integer n, you can verify that these will always satisfy Laplace's equation. And that would probably be a really, really good idea to prepare for like the first week of next quarter. Okay. Yeah, great question. let's see. So there's a few things I want to tell you that get back to Stokes' theorem and Gauss's theorem, because these are really, really useful. And what we're going to do is, essentially I'm just going to restate what it means to have zero divergence and zero curl. Okay, so if I have my vector field and it's doing something, can't really draw this that well, but I have some vector field that's doing its thing, okay? And let's say that I take a big closed contour integral, like this, a right-handed, is that right-handed? That's left-handed. Well, I'm left-handed. So let's say I take a big contour integral, C, and I integrate various quantities. I either calculate what is the flux through this contour C, or I say what is the integrated tangent component of the velocity around this circle. And we're going to find that those quantities are really, really important and are equal to 0 for conservative potential flows. Okay, so the integral around C of my velocity field dotted with, and I'm going to define some things. I'm going to define a tangent vector u, and I'm going to define a normal vector n. Okay, tangent to the curve and normal to the curve. So if I look at the component of my velocity field that is tangent to the curve, and I integrate that across the whole surface, the whole boundary of the surface. So what theorem do I use to simplify this? I'm basically looking at how much of my vector field points in the tangent direction, and I'm adding up all of those components around this closed circle. Okay, how many of you think it's Gauss's theorem? How many think it's Green's theorem? How many think it's Stokes' Green's theorem? Okay, I'm not getting enough hands. There's no conservation of hands. Those are the only theorems I taught you. So this is a Stokes theorem problem. Okay, so what that tells me is that this is equal to the the area integral inside C of the curl of V times some larger, this kind of little surface patches, dA, if you like. But what do we know about the curl of this vector field? 0 everywhere. Okay, it's 0 everywhere. So this equals 0 everywhere. That's kind of cool. That tells me that if I take and integrate the tangent component of this over any closed contour C, whether it's teeny or huge or in the right half plane or in the left half plane, it's always going to equal 0. That's a pretty powerful statement. And we know this because our potential function satisfied Laplace's equation. Actually, really just because our vector field V is the gradient of a potential. That's all we need. Okay, another one. Let's say, so this is called the circulation. And it makes sense because it would tell you how much this flow is circulating. If I had a big vortex here and I integrated around that contour, then I would actually get a positive number or a negative number. So circulation is really, really important for aircraft. If you get on an airplane and the airplane wings don't have circulation, get off the airplane. Okay, flux. So let's say that we want to compute the flux of this vector field out of this contour C, or through this contour C. So what I want to know is this vector field, is this flow, is it carrying fluid? Is there a net inflow of fluid, or a net outflow of fluid, or is there a net balance of fluid, or of mass, or of whatever we're advecting in this vector field? It's called advecting because you're moving it through a vector field. Convecting, vect is vector. So the flux is the integral around C of my vector field dotted in the normal direction, ds, right? I'm going to integrate this around C. So this is the amount of stuff that is coming out of C. And how do we solve this integral? Okay, Gauss's divergence theorem. So what does Gauss's divergence tell me that this has to be? So a volume, or a one-dimensional higher integral over inside of C of what? Divergence of V dA, and that also equals 0 because we have this special potential flow. So this tells me that no matter where I start with a blob, I don't have a net inflow or outflow of material into that blob. And it's also kind of cool that if I take this blob and I flow it, its volume is going to stay the same. That's also what it means. So this one is true for any V that's given by the gradient of any scalar potential phi. Doesn't have to be a special function phi. This first circulation equals to 0 is true for any gradient field, period. Right? That's a vector calculus identity. Curl of grad of anything is 0. This second one is a more special condition. This is true for V equals grad phi, where the Laplacian of phi equals 0. So for this flux equal to 0, I need phi to be one of these special Laplacian equals 0 phis. Good. Okay, more questions about this example. Okay, I can't restrain myself. I'm going to tell you what happens if I mess everything up and I say that my potential function phi is 1 over z, or log of z, or some nasty function of z that has singularities at the origin. So if I had some function that was singular at the origin, probably 1 over z is not the right one. I think it's 1 over z squared, or log of z, or something like that. Say or log of z. Then what I might have is I might have a vector field that looks like this. I might have a vector field that has some rotation, which is a problem. That means that my circulation is not equal to 0. Right? If I integrate over this contour C, the tangent component, it adds up to something that's non-zero. This is what we want if we're going to be in an airplane. We want our airplane wing to be essentially a streamline with positive circulation. And so it means that my curl is not equal to 0 everywhere. And it means that my vector field is not a potential, the gradient of a potential. Okay? That's a problem. But it turns out that I might still have a stream function that I can use to compute the velocity field. Okay? So the potential part guarantees that I'm irrotational, because grad of a potential is always going to be curl-free. The stream function part guarantees that it's incompressible. So the fact that there exists a stream function is really what's guaranteeing that I have incompressibility. So the next example I'm going to show you is kind of a degenerate potential flow. And degenerate potential flows are actually what we're interested in from engineering situations. So what we do is we take a relatively well-behaved vector field that's curl-free and divergence-free, and then we give it a singularity at a couple of points. We put vortices or some kind of singularity in at a few points, and that gives our system a little bit more physical use, like airplanes. So for an airplane, the discontinuity at the tail, the sharp trailing edge, is where you get all of the circulation from. Because if you didn't have some circulation around your airfoil, you would essentially have an infinite velocity where the flow tried to turn the corner around the tail of the airfoil. I'll tell you about this later. So let's take this stream function psi of x and y equals sine of pi x and sine of pi y. And let's look at this on a domain which is from 0 to 2 in the x direction, and from 0 to 1 in the y direction. Okay, so we're going to look at this in a little rectangle. 0, 1, 2, 0, 1. We're going to look at this, the vector field from this stream function over this domain. Okay, this is D. Okay, so the first thing we can do is compute a vector field V. Okay, so V equals V1 and V2. Now, what are V1 and V2 in terms of my stream function? Partial psi, partial y, and minus partial psi, partial x. How many of you have seen Lagrangian mechanics and Hamiltonian mechanics? Some of you, okay. This is starting to look a lot like a Hamiltonian. Okay, so the stream function, level sets of psi is basically the same as a Hamiltonian function. Okay, you get a vector field from taking this weird skew symmetric partial derivatives, and level sets of psi are energy conserved surfaces. Okay, interesting. So this is equal to partial of this with respect to y is pi cos of pi y. So that's pi sine pi x cos pi y. And pi minus pi cos pi x sine pi y. Okay, not too bad. And if we want, what we can do is actually bring this up in MATLAB. So this defines a vector field. This defines, I don't remember what it doesn't really matter, but I think it basically defines a vector field that looks like this. So I have this kind of rotational cores, and they're going in equal and opposite directions. Okay? So this could not be the gradient of a potential function, because this has curl, non-zero curl. But it is divergence free, so I can define it using a stream function. Okay? And what we're going to do, I don't have time today, so I'm not going to push it. We're going to code up this vector field, for example, in p-plane. Right? In p-plane, I could literally type x dot equals this function of x and y dot equals this function of x and y, and I'm going to get a vector field that looks like this. And I can drop particles in that vector field, and I can see where those particles are advected, and they're going to go in these funny little closed contours. Okay? So what we're going to do on Friday's lecture is we're actually going to code up this. It's called the double gyre. Gyre just means rotation. This is a double gyre vector field. We're going to code up the vector field that comes out of this fancy stream function. You can verify that this is, in fact, rotational. This does not have curl 0, but it is incompressible. And then what we're going to do is we're going to start making this time dependent. So we're going to make this a function of x, y, and time by putting in a time-dependent frequency f. And what that's going to do is it's going to slosh the gyres back and forth. So one's going to get bigger while the other gets smaller, and then they're going to alternate. So the other one gets bigger. And this is a model for ocean mixing. So you have big vortices and big currents and circulations in the ocean. And depending on the seasons and the sun loads, some of them get bigger when others get smaller, and they slosh back and forth. And we're going to integrate particles through this induced vector field. So we're going to solve the ODE for what a particle does. And we're going to get some quantification of what the mixing in this simple ocean model looks like. So this is a real research problem. With collaborators, we've written papers on this. This is something you can actually start using. I'll give you the code, and you can actually do research on this problem if you're interested. Okay, that's where this is going. I'm going to hand out the midterm online after my office hours in 1 hour. Okay, thank you.